Welcome to next lecture of compiler design. We will discuss where we will continue machine independent code optimizations and we will discuss runtime administration. I am Dr. Parul Yadav, assistant professor at Department of Computer Science and Engineering in Institute of Engineering and Technology, Lucknow. Now, here we will discuss, we will continue the code optimization techniques, machine independent code optimization techniques, then we will discuss runtime environment and then various data storage allocation schemes and then we will focus simple stack allocation scheme. So, first we are continuing in the previous class, we have already discussed the source program and its 3 address code. Then we obtained the flow graph for the obtained 3 address code and then we discussed the optimization technique like local common sub expression as well as we discussed elimination of global common sub expression where from block B5 and B6 we eliminated global common sub expressions. Now, we are continuing the optimization techniques. Now, next code optimization technique is copy propagation. So, we may have the assignments of the form u is equal to v and such assignments are called copy statements or copies. So, we can use v for u wherever possible. After the copy statement u is equal to v. So, if such statements are there, this is just the copy statement is there. So, in subsequent steps we will prefer to use v rather than using u. So, just see, suppose we have this arithmetic expression and this arithmetic expression and then this is actually the flow graph. Here we are computing d plus e, here we are computing d plus e and in this section again, in this block again we are computing d plus e. So, what we can do here, we can take the computation in the variable t and then we can assign this t to a. So, this we can say this is a type of copy we have and then here what we have again we are doing the computation d plus e is equal to t and then we are assigning this t to b. Now, here what we are doing, here we have the expression of the form u is equal to v, we have the expression of this form. Now, here rather than doing this computation again, what we will do? We will just copy the value over here, mean the variable that is doing, that has done the computation earlier. So, we can write here c is equal to t. We will see this example in our block, just like the block 5 that we obtained over here. This is the block 5 and this is the block 5. Now, in the block 5 we can see x is equal to T3, this is okay. Now, a at T2 is equal to T5, this is also okay. Now, look at here, a at T4 is equal to x. So, what we can say, x is equal to T3 is a statement like u is equal to v. So, what we will do in coming in the subsequent statements, we will prefer to assign value of v rather than u. So, here rather than using x, we will use T3. So, a at T4 will equal to T3, right, and last statement will remain the same. So, this is the outcome of copy propagation, right, copy propagation. Next is the dat code elimination. Actually, why we did so, here you may be feeling that the number of statements here and here are the same, but here actually some optimization has been done. How it is done, that will be visible in this particular step. So, this step is dat code elimination. So, we know in the program we may have the dead variable or live variable. I am repeating what is live variable. If its value can be used subsequently in the mean, it can be used in subsequent statements of the program, then that variable is called as live variable, otherwise it is considered as dead variable. Similarly, we can have dead code in the program. What is dead code? These are the statements that compute some value, but that value never get used in the program. So, such statements are such statements are called as dead code. So, here just see x is equal to T3 and this and this and this and this. in this block we can easily find that here we have written one statement x is equal to T3, and within this block x is nowhere used, it is not used in any statement. So, we can consider this statement as that statement or that code. So, we can easily eliminate this statement. So, here we will have only 3 statements, AKtU is equal to 5, AKtU4 is equal to 3 and go to B2. How we have obtained it? Because this is because of the outcome of copy propagation. Here we eliminated, we have not written x, we have written here T3, and because here we are not written x, that is why this has become useless now. So, we can eliminate it, and here we are finding we have reduced number of steps, number of statements, because we have removed here the dat code. Now, next is another concept is constant folding. What is constant folding again? Constant folding here. Now, suppose I have a variable, suppose pi underscore 2, and suppose this is equal to 2 into 3.14. So, actually this statement is computing some constant value, and then that value is assigned to variable pi underscore 1. So, what we can do here, we can replace the variable by the expression. So, here this expression has some value that is actually constant value. So, we can replace the variable using the constant directly. So, in place of pi underscore 2 we can directly write its value. So, at the compile time only we can detect such expression that are giving the constant result, and we can replace it with it using the constant only. So, detecting at the compile time that the value of the expression is constant and using the constant. So, this is known as constant folding. Now, next is code motion. Code motion means this is very important section of the program. The important section of the program is the loop that we have, and if we have loop may have many statements, and some of the statement may be having some computation, and that computation may not be required to do inside the loop, that can be kept outside the loop also and will give the same computational result. So, such statements are called as loop invariant statements. Such statements can be kept outside the loop, and in turn they will reduce the running time of the program. So, it improves the running time of the program by decreasing the length of code of its loop. So, we will place loop invariant computation outside the loop. Now, see one example. While I is less than or equal to limit minus 2. So, actually limit is one some variable, and here it is not used suppose inside the loop, and here we are just every time we are computing it and then we are comparing the value. So, in this loop will be executed many times in the program, and every time we will do the computation. So, what we can do, we can keep this statement outside the loop like t is equal to limit minus 2, and then we can compare I with t. If I is less than or equal to t, then we will execute the loop. So, this is the code motion technique. Now, next is reduction in strength, where we try to replace the costly operator with the cheaper one. So, we can see over here, like here we have, just see in this particular block, right, this block. Here we have j is equal to j minus 1, T4 is equal to 4j. So, what we can do, here we are taking some value of j and then we are multiplying it with 4, and every time it is reduced by 4. So, what we can do, we can write here like this, t is equal to T4 minus 4. So, here we have changed this multiplication operator with minus operator. So, we reduced the, here we have reduced the, we have replaced the costly operator with the cheaper one. The same can be done here, the same can be done here, and every other place. So, this is about reduction in strength. And now, this give the concept of induction variable. How it is giving? Here we are having just see two variables I and j. So, initially what we are doing, we were computing value of T2, T4 using j. right. We are computing value of T4 using J. So, these two J and T4, they are called as inductive variable. Now, what we did it, now we are writing T4 in terms of T4 only. So, this is now we have written T4 in terms of T4 only. So, we can eliminate J is equal to J minus 1 from here. So, we can write only T is equal to T minus 4 and then remaining two statements. So, if whenever sometimes we will be doing reduction in strength and we will find that we are able to remove the induction variable. So, this is the concept of induction variable. So, this completes our machine independent optimization techniques. Now, we will discuss the next topic, that is the runtime environments. As far as compilation is concerned, so during the compilation, the compiler must allocate resources of the target machine to represent the data objects that are manipulated by the source program. So, compiler needs to allocate resources for various data objects. Now, data objects can be elementary data, they have elementary data types, or they could be of form, they could be like aggregates. So, elementary data type mean like data objects like integer, float, character. So, they are actually elementary data type and they are represented by equivalent data objects at machine level. Now, next is the aggregates like array, string, structures that are comprised of elementary data types. So, they are represented by several words of machine memory. So, this is a runtime environment. Now, if we talk about data storage allocation scheme, so broadly we can say there are two types of data storage allocation scheme. One is a static data allocation scheme and second is dynamic data storage allocation scheme. So, in static allocation scheme, it is done actually at compile time only. So, the compiler allocates space for all names, it could be global or it could be local. So, all variables of all procedures at the compile time. So, here the space is allocated for all type of names at the compile time only. Now, the variable SS is fast in case of static data allocation and it does not support recursion. Now, next is dynamic data storage allocation scheme. Here the compiler allocates space for names that are available in the program. It allocates compile time as well as run time, compile time as well as run time. Here variable SS is slow and it can implement recursion. So, broadly there are two types of allocation scheme and in today's lecture we will focus on static data allocation scheme, data storage allocation scheme. So, we use the stack implementation, we use stack to implement the static allocation scheme. So, if we talk about the variable, then there can be two types of variable, one is the global and second is the local. So, global mean they allocated static storage and they are available to any procedure. So, they are globally defined, available to any procedure defined in the program, and the local mean they can be accessed only by the procedures in which they are declared. So, this is the local variables. Now, here we talked about the stack implementation and it will look like this, where we will have the static area and the space for the various procedures. So, it will have the space for activation record as well as extra space, extra storage for every procedure, that we will discuss in coming slides. Now, next here we have each procedure has an activation record on the stack. So, basically we can say that the data is data can be global or static. So, this is the space for global or local. So, this is the space for global or static data. Now, next is in the program we may be having various procedure and each procedure will have its activation record. So, we will have the activation record, suppose procedure is P, procedure is Q, procedure is R. So, we will have record, we will have entry for activation record for P, activation record for Q, activation record for R, and everywhere we will have extra storage for every procedure. Now, it keeps value of the local names. So, this keeps the value of local names. So, here we can say the two segments are there, one is the low numbered memory location. So, we can say this one, and second is the high numbered available location. So, we can say at this position. So, at the low numbered memory location we are assuming this is at low index and this is at high index. So, at low numbered memory location we store the global or the static data, while at the high numbered available location we store the runtime stack, and here it is just like this. So, here we store the runtime stack, and low numbered memory location, this is a place to store various procedures or the space for global data. Now, next is we can see that this is the space for global data or various procedures, and this is the for the time stack. So, we can say observe here that there will be the gap in between the static area or global area we can say and the runtime stack. Now, here what we are doing, here we have the space for global or static data, and next to it mean in the runtime stack we have the activation record and storage space for various extra space for various procedures. So, what is the what we are assuming here, that we have the procedure P, that is our main program. It is calling procedure Q, and which in turn is calling procedure R. So, the P will be at the bottom, and then above to it we will have Q. Now, Q is calling R, so it will come over here. So, everywhere we have activation record, space for activation record and extra storage. Now, here we can see the organization of the activation record in C programming language. So, we can observe that broadly there are 6 fields here. This is the stack pointer, and stack pointer is pointing to this particular record, that is old stack pointer. And here we have the fields like local data, old stack pointer, return value, return address, argument count and actual parameter. Now, here you can say that here we have the pointer, that is top pointer, and this is our stack pointer. Now, next is top and stack pointers. We will slightly discuss these pointers. So, they are actually permanently allocated registers. Now, stack pointer, that is written over here, stack pointer, it points to particular position in activation record for the currently active procedure. And what is top pointer? It points to the top of the stack, like in this case, it points to the top of the stack. If it is calling to next procedure, then top pointer can be decreased and the next records can be kept over here. So, this is the top pointer and stack pointer. Now, we will go into some details what the activation record is having. Here we have the 6 fields, basically this is for the local data. Next is the value of the actual parameters. So, all the values of the actual parameters will be kept here. Next is the count for the number of arguments, it will be kept here. If we are talking about procedure, then it will be returned from some address. So, return address will come over here. Then the return value, if the procedure is returning something, then we will return value will come over here. Initially we keep this cell as blank. Now, or we keep the space for storing the return value. Now, value of a stack pointer for the activation record. So, this is the value for the stack pointer for the old activation record, for the old stack pointer. So, these are the broad entries, and here we have the stack pointer. Now, next is the stack pointer and the offset. So, stack pointer, negative offset and positive offset, what is the concept here? Usually or generally stack pointer initially points to old pointer. So, old pointer. So, mean if we want to fetch this particular record, then we can fetch it from this index. If we want to get the return value, then we can increase the index and we can fetch the all relative indices. We can get the data from our indices. Now, if we want to fetch the local data, in that case we have to decrease the offset. So, rather here we will be fetching the local data through negative offset. So, here we will provide the negative offset. Now, next is a positive offset. Positive offset mean in that case it is actually suitable, useful for base register machines, where the stack pointer will point over here and there will be no concept of negative offset. Every time we will be using the positive offset to fetch the respective values. Now, next is, if we are talking about offset and stack pointer, then another concept is x at SP or SP at x. So, here actually this x is offset, or we can say the constant, and this is the stack pointer. So, this x tells us the distance of the location for x from the stack pointer. So, it is just like in the stack pointer x is telling us the location or the offset in SP with respect to SP. So, but we can write it like this also, x SP, mean this is just the offset of SP only, but the notation is like this. In some of the compiler, this can be written only as x. Meanwhile, designing the intermediate code, in some of the compiler it can be written like x only, and now it is left to the code generation phase to realize that x is on the stack, right. Now, next is SP at x. So, here x is actually the offset, and this is the array, we can say the stack that we are having, the pointer to the stack, and this actually shows that this indexing is commutative in nature. Commutative, as we can say that SP at x and x for SP, they give the same value. In terms of computation, indexing is commutative in nature, but there is difference in these two notations, as this and this. So, difference in loading in register. So, if we are using this syntax, then it will require only one step for loading it into the memory. Now, if we are using this one SP at x, then it will require two steps to load in the register. Why it requires two steps? Because one extra step will be required for loading of offset into the register. So, first we will load this offset into the register and then we fetch the value from that particular index. So, this is about stack pointer and offset. Now, we will see if we have suppose procedure in the C program. So, it will be having various parameters, then we have call P and N, such type of syntax is used in 3 address code representation. Okay, sorry. So, this will be used. Now, we need to see how the object code will be obtained, how the runtime code will be obtained for such type of instructions. So, here we translate each parameter T into push T. So, wherever we have T1, T2 and Tn, they all will be translated into push T. Now, how the actual translation will take place? Push x implies, here the single push x implies we will decrease top is equal to top minus 1, and then we will set value at top is equal to x. Pointer to top is equal to x. Now, here we are considering, we are assuming that we are placing T1 at highest index and then Tn at the lowest index. As the parameters will come, we will decrease the top pointer, top value, and we will keep on pushing all parameters onto the stack. Now, next is to see how we implement, translate call P comma n. So, here actually this translation requires to store many things into the stack, like argument count, return address, return value, old stack pointer, and then we will move to the first statement of P. So, this will require many things to be pushed onto the stack. So, we will push everything onto the stack like push n. Push n will store argument count into the stack. Now, push L1, this will store label of return address. So, this will be pushed into the stack. Next is push, this is the space for return value. After execution function will return value. So, we will keep it a space into the stack. Now push SP, that to store the old stack pointer. Then go to L2, it will move the first statement of P, and we are doing all in the same order as we have designed the activation record. So, they are like this. Next is, in the program when we will write the procedure, every procedure will begin with proc begin syntax. So, this is the first statement for every procedure. So, we need to translate the first statement also. Now, this sets actually the stack pointer to the place holding the old pointer. So, it sets the it. Now, sets the top to the top of the activation record. So, what we will do? We will set SP is equal to top, and then we will set top is equal to SP plus a small sp. Sp is the this is the size of P. So, it is a number of words taken by the local data for P. So, this will be top is equal to Sp plus a small sp. So, this is with respect to procedure begin. Now, once we will begin the procedure, then we will have many statements, and last we will have the return expression. Now, we will see how to write the object code for return statement. So, it will be done like this. So, this is for return statement. First SP mean this is offset here, this is equal to top. So, 1 is the offset for the location of the return value. Now, next is we set top is equal to SP plus 2. Now, top points to the return address. So, we can see as here. Now, this is pointing to return address. Now, next is SP is equal to a value at SP. So, it restores SP. Now, we will set here value of L. Now, this will be now the return address, as it is pointing to return address. Like here we set the top to point to return address. Now, L will have the value of return address. Now, we are increasing top is equal to top 1 1. So, actually here we are taking the this is a return address. Now, we are taking next with this index, now we are taking the argument count. So, we are increasing it by 1. So, we can take it points out the argument count now, and next is top is equal to top plus 1 start top. So, this is actually the number of parameters of P. So, we restore top to the top of extra storage for activation record below. So, we will setting it considering the extra storage space, considering its number of parameters. Now, next is go to star L. So, here this is the translation for going to the return address, as we have taking it into this L, the return address. So, this is the translation for return expression. Now, next is the last thing in this, we will every procedure will end by the procedure AND call. This is written in 3 address statement like this. So, end of the procedure can be marked by the 3 address statement, and this is actually translated as we discussed before, but excluding the storing of the return value. So, this is all about the static stack allocation scheme, where we discuss this implementation scheme using stack. So, this is all for today. Thank you.